In question 8, we start off with the Euclidean geometry. All the info that's been listed is given on the diagram, with the exception that BC is a tangent to the circle. I like to mark that off. It just helps you apply theorems a little bit better if you mark that off. Your brain can see it a lot faster. So to get A1, we're going to apply the tan chord theorem. Let me show you what that's all about. So the tan chord theorem states you have equal angles that exist between the tangent and the chord, as well as the angle that is subtended by the chord. So you follow that chord down to the circumference, and then you get the angle that will be equal to this one. So if we apply that here, our chord is dB. And after recognizing our chord, we follow that down to the circumference. And when we follow that chord down to the circumference, it takes us to A1. So A1 will be the same size as this angle between the tangent and chord, which is 22.5. And now we've successfully applied the tan chord theorem. Okay, so how we write that is quite easy. We simply just state the size of A1 to be 22.5, and then we list the reason to the right of it, the tan chord theorem. And then this question is worth 2 marks. You get 1 mark for your statement and 1 mark for your reason of the tan chord theorem. In the next question, we need to find the size of D1. And D1 is located over here. So I'm seeing something happening quite close by. I see an isosceles triangle. So let's use that to our advantage. So the theorem we apply here, if we have equal sides in a triangle, then we have equal angles located at the base of the triangle. So I know that this angle C is the same size as this, 22.5. And when we state that C equals 22.5, we're going to use this as our reason. Angles op equals sides. And now to get D1, we're going to use exterior angles of triangle, because D1 is the exterior angle of triangle CDB. And just to walk you through that theorem, to get the exterior angle, you go to the opposite interior angles, add them together, and then they give you this outside one. So you can see in this example, 40 plus 70 gives me this 110 degrees over here. So to get D1, we go to the opposite 2 interior angles, add these guys up, and we get D1. So 22.5 plus 22.5 will give me an elegant 45 degrees over there. And this is the best way to write it up. You just state D1 equals the opposite 2 angles added together for the reason of exterior angle of triangle, and then you just simplify that. You can also pop it into your calculator to triple check, and we get D1 to be 45, which I have indicated on the sketch. And your 2 marks in this question are awarded from the statement and reason in this first line with the angles opposite equal sides. It's a fancy way of saying isosceles triangle. And D1 equals 45, 1 mark gets awarded for that statement, actually answering what they asked you to. 8.1.3, we need to get the size of B2, which is sitting over here. Okay, and now I recognize B2 is touching this line. This is quite a special line. It's a radius. And there's a very commonly used theorem with a tangent and a radius. And that theorem is called tan perpendicular to rad. It's not the first time we've seen it in this paper. So if I have a radius and a tangent that are touching each other, there's a 90-degree angle that exists in between them. So I know that there's a 90-degree angle over here. And then if I want to state that in my work, I've got to say the angle OBC is equal to 90 degrees. There's a lot of angles at B, so you've got to be very specific as to which one is 90 degrees. And when you list OBC, just make sure to put a copy over the B. It's kind of telling the person marking your work that the angle resides on the letter B. So the angle is by B over here. And then to get B2, we know that both of these, this 22.5 as well as B2, added together, they give us 90. So it stands to reason to get B2, I can just say 90 minus 22.5. And don't take chances with that, just pop it straight in your calculator and it will give us 67.5 degrees. And the 2 marks in this question come from the correct reason of saying tan perpendicular to rad, as well as your final answer of 67.5. This line does not need a reason, just by the way. In 8.1.4, we need to get the size of O1. O1 is sitting over there, and it's at the center of the circle, which is quite a big clue as to which theorem we're going to use. Now, if we have an angle at the center and an angle at the circumference, we can apply the following theorem. The angle at the center is 2 times the size of the angle at the circumference. It's a little bit difficult to see with this one, but it kind of looks like a bow tie. And with this bow tie, you've got 3 points on the circumference and 1 point is at the middle of the circumference. So this one at the center is 2 times the size of the one at the circumference. If you kind of follow this 45 back down to its chord, you get to BA, and then you can follow BA back up to get to O1. So this 45 and the O1 are subtended by the same chord. So we can just jump ahead and say O1 equals 2 times 45 for this reason over here. Angle at center equals 2 times the angle at circumference. Just like this, and 2 times 45 will give me a classy little 90 degrees over there, boss. Alright, let's fill that in and move on. And just before we move on, one thing teachers do appreciate is just stating the relationship with the letters first. So saying that O1 is 2 times the size of D1 and then actually filling D1 in as 45 degrees. Yeah, the teachers do appreciate that. It is good to put in your work. Okay, the 2 marks. One mark comes from the reason, and the second mark comes from the answer of 90 degrees for O1. In 8.2, we've been asked to prove that line OA is parallel to CB, and you've got about 4 ways of doing that. The best place to start looking is to prove one of these 3 things. So if I prove the corresponding angles are equal, so like if I make an F and I prove that these angles are equal, that adequately proves that the lines are parallel. Conversely so, if I prove that the co-interior angles add up to 180, that will also prove that the lines are parallel. And lastly, if I prove the alternating angles are equal, that will also adequately prove that the lines are parallel. So what I normally do is I highlight these 2 lines and see which one of those I can create. So if I highlight those 2 lines, I can't really make an F anywhere. If this line was extended, I could make like a sideways F, but that's not happening. I can make a U, but the problem with that is I don't know A2 and B1, so that's going to create a lot more work for me. But I can just join up these 2 lines to create a Z. And if I do that, would you look at that? The alternating angles are already equal. B2 is 90 degrees and O1 is 90 degrees. So we're definitely going to be heading down this route. The alternating angles are equal. And we just start off by showing that we recognize that those 2 angles are equal. So we're going to say angle O1 is equal to angle OBC. And we did prove that they were both 90 in previous questions. So you can see we proved O1 was 90 in this question. And for 8.1.1, or one of these questions, sorry, it was in this one, 8.1.3, we proved that OBC was 90 because of tan perpendicular to rad. So we've proved this above. So what we put down as our reason for this statement is proven above. And now we can jump to our conclusion that OA is parallel to CB. And our reason for knowing they are parallel is the alternate angles are equal. So we put this as our reason over there. And having a look where the 2 marks come from, this statement showing the link between the alternate angles gets you your first mark, and the reason of the alternating angles are equal gets you your second mark. And 8.3 gives us the length of the radius to be 12 units, and with that we've somehow got to calculate the length of BC, the tangent. So we did recognize earlier that this is a radius, so that will have a length of 12 units. And then I see another sneaky little radius over here, OA. Okay, and let's go through how we express that to our teacher. We just say OB equals OA equals 12 units radii. And I'm also noticing both of those are in a 90-degree triangle. And a 90-degree triangle is the nice side of town. I've got 2 tools at my disposal. I can either use Pythagoras or I can use SOHCAHTOA. Since I don't have any angles inside of this triangle, OBA, I'm not going to use SOHCAHTOA. I'd rather use Pythagoras because I've got 2 sides and I'm missing the third. So I'm going to calculate BA with the use of Pythagoras. Now my hypotenuse is the side AB, so I'm going to fill in AB in the hypotenuse's place. And just how to structure your work, you want to put Pythagoras as your reason. So I've just put Pythagoras over here. And then the other 2 sides just get filled in over here, so that's the 12 and the 12. So I'll put 12 in over there and 12 in over there. Okay, and then 12 squared plus 12 squared, I believe it's 288, but let's double check it with our calculator. So you just pop that in, press equals, some crispy mental maths there. Okay, so AB squared is 288, and then I'm just going to square root both sides to get AB on its own. So if I just square root 288, it's going to give me the length of AB to be 12 root 2, and I'm going to leave it in that format. Okay, we are getting somewhere. Now I somehow need to link this side to this side, and we're going to do that using the triangle ABC. It's quite a special triangle if you haven't noticed already. The base angles are the same, which means that these 2 sides must be the same length. And the Euclidean geometry rule that dictates that if I have equal angles down here, then those 2 sides must be equal. So I have equal angles over there, which means that BA must be the same length as BC. And we do have to kind of state a few things to convey that message to the person marking our work. So firstly, we need to show that we recognize the angles are equal. So I'm going to say A1 equals C, and that was proven in previous questions. We got this 22.5 and this 22.5 from previous questions. So we're going to use the reason proven above. And we state it just like that. A1 is the same size as C, which is 22.5, and we did prove that above. And now we jump into our conclusory statement that AB has the same length as CB, and we just simply say AB equals BC. And our reason for concluding that is what we spoke about earlier, sides opposite the equal angles. So this side is opposite that equal angle, and this side is opposite that equal angle. And now we have the length of BC, and we've successfully answered what they asked for. And I also like to be a bit overly cautious with these questions. I like to give the decimal value as well. So if I just press S to D, I'm also going to say 16,97 units underneath the root or the surd form. And lastly, we're going to have a look where our 4 marks come from. The statement and reason for Pythagoras gets you your first mark. The answer for AB gets you your second mark. The statement and reason for the isosceles triangle, saying that this side equals that side, gets us our third mark. And the answer of, you can either do the surd form or the decimal form, will get you your 4th mark.